This is Mrs. Palmer-Quay with the second video for Module 8. In this video, I'm going to talk about several key periodic properties that have been part of the organizational background for the periodic table. Remember that your periodic table is arranged by increasing atomic number. Furthermore, the elements are grouped together, first in columns or groups of elements that share chemical properties, and you should now be able to recognize that these chemical properties are determined by the arrangement of the valence electrons, and that the rows of the periodic table also have an arrangement where the highest energy level for the electrons of all the elements in that row is the same. The orbitals are also sometimes called electron shells. I just threw that in there for a little bit more background information for you. So this general organization can also be elaborated to look at some particular trends that repeat their way across a period or down a column. And this repeating nature is called a periodicity. That's part of the reason we have this periodic table. We're going to talk about ionization potential, electronegativity, and the radius of neutral and ions of the atoms. So the first one I want to talk about is ionization potential, also known as ionization energy. And this is the amount of energy needed to remove one electron, that first electron, from a neutral element and turn it into a positive ion. In general, elements that have fewer valence electrons or are just a larger atom in general, they have a larger number of electron shells, a larger number of orbitals, will have a lower ionization energy. So as we go across the periodic table, we are moving towards more valence electrons, and so we need more energy to detach them. And as we move down the periodic table, we are down a column in the periodic table, we are moving to elements that have more electron orbitals, more shells, more energy levels, and so it becomes easier to detach them. So this far corner down here with francium is the element that it is most easy to get that first electron off. And this element fluorine over here, the other F, is the element where it is most difficult to get the first electron off. We're basically going to discount the noble gases because they don't react, and those electrons are even harder to get off, but because they don't react, we're going to ignore them. And so as we move across the periodic table, the amount of energy we need to remove those electrons increases, and as you move up any column it increases, or as you move down it decreases. We can use this trend to compare two elements. For example, if we compare magnesium over here, the ionization energy as oxygen over here, we can see that magnesium is more to the left of the table, oxygen is more to the right, and so oxygen would have a greater ionization energy than magnesium. Electronegativity is the flip side of ionization energy. It's not how much energy is needed to take an electron and move it away, but it's a measure of the ability of an atom to attract an electron, to pull that electron to it in a chemical bond. Because they're sort of flip sides of the same, what's happening to the electrons, the arrows, the pattern is the same as ionization energy, again, not including the noble gases. So electronegativity, the ability to attract an electron, increases as you move to the right. So again, fluorine over here is the most electronegative molecule. It has the strongest pull for anybody else's electrons. And as you move up any particular column, the electronegativity also will increase. So down here in this corner, these are the least electronegative elements. They are the ones that are not going to attract an electron from some other element. In fact, they are the ones that are most likely just to give up their own. So electronegativity is very similar to ionization potential in the way that it is arranged on the periodic table. And then we have atomic radius. That is the distance in the, it gives you a measure basically of the size of the atom. It's not a very precise measurement because it's difficult for us to make measurements on atoms, but in general, the radius will decrease as the atomic number increases. So as you move across any particular period, as there are more and more protons in the nucleus, somehow that seems to pull those electrons in more tightly. Even though you still are having a balanced number of protons to electrons, the atomic radii seems to be decreasing as you move across. As you move down any column, you are adding more energy levels, and as it might, this one seems at least a little more logical, that the atoms will get larger as you add another energy level. So when you're going across the table, things pull in more tightly as you add more protons, and so atomic radii decreases moving to the right, but it increases as you add more energy levels as you go down any particular group. If you turn those neutral atoms into ions, either positive or negative, they are differently sized than the neutral element. Metal ions, which will generally take on a positive charge, end up being smaller than the neutral atom of their element because they have lost an electron, and so the number of protons is now one more than the electrons, and those protons can really pull those electrons in tightly. So on this example table here, the ion is shown in darker gray, and so you can see in our metals, the dark gray is this dark gray center spot on the circle. So that dark gray shows the size of the ion, the positive ion, where that extra proton just really helps snug in those electrons. So with the metal ions, the positive ions, they are smaller than the neutral element version of the atom, but nonmetals are the other way around. They have a negative charge because they have picked up an extra electron, so there are more electrons than protons, so those electrons are just able to escape a little more, to kind of pull out from the nucleus a little bit more, and so the ions are larger, shown over here again by the dark color representing the ion size. So we have a dark ring around these particular ion comparison to the neutral atom instead of a dark center like we have with the metals. So if you just think about it, it makes sense because of the relationship between the positive and negative charges and the forces of attraction. So those are just some of the key periodic trends that helped scientists put together the periodic table, and we can use those periodic trends to make some predictions in comparing different elements. That finishes what I wanted to cover in this video for the second video of Module 8.